Now, today we're going to see graphs one session. Okay. So, uh, we're going to check what is graphs. Right. Someone is joining, I think. What is graphs and how to represent the graphs. Okay. And later traversal of graphs and some applications of traversals. Okay. Applications of this traversals. Okay. I will start. What is graphs? Suppose you have some elements or some objects, okay, and you need to store the relationship between them, okay. So how many of you know the relations in math, like functions, relations, right? You might have studied functions, and you also might have studied relations also, right? How many of you know what is relations? Okay, so you can unmute and tell because I can't able to see the chat. Okay. Now, what a relation looks like, there will be some elements, okay, and there will be a relation between them, like this one relation, like this one relation, this is one relation, this is one relation, and this is one relation, and also this is one relation. So this object can relate with the multiple objects. Here, see, this object is related to this, and this, and this one is related to all the other objects. So uh, this is the relation. Now, how do you store it in a data structure? Okay, how do you tell or how do you make computer understand this relation? So for that we use graphs. Okay, so actually the purpose of graphs is we have several objects, and we need to store the objects and the relationship between them. Then we choose graphs for it. Okay, uh, and there is certain terminology in graphs. First one is node. Second one is edge. First, let's say these two. Okay. Uh, Till this, it's fine, right? What is graph and why exactly we use it? You guys understood, right? Hello. Hello. You can just unmute and tell me because I can continue then. Hello, guys. No one has understood this. Hello. Hello, Vaibhav, Subhashish, Madhu, Apratin, Himadri. Not audible. Do you understand what is graph? Like I told now. Hello. Voice is not clear. Okay. Fine. Let me use. Now tell me, is the audio clear?
Yes, Bhaiya.
Okay, great, fine. So just respond because then only I can able to know, right? So again, I will tell what is graphs. You know what is relations in maths. You have certain objects and there will be relations between them. Here, this object is related to these three objects and this one is related to all the other four. Like this, you might need to store this in a computer. Like you want computer to understand this relation, then how you can do it? So then graphs we use. So basically we use graphs for representing a relation between different objects or multiple objects. And before moving forward, there is certain terminology that you need to understand in graphs. The first one is nodes and the second one is edge. What is node? So node is every object that we are talking about is a node. Okay, this is a node, this is another node, and this one is a node. Okay, so you understand what is node. And now what is edge? So this relation is called an edge. This is an edge, and this is an edge. So how many edges this graph has now? One, two, three, four, five, six. So six edges it has. And how many nodes it have? One, two, three, four, five. Okay, so it has a five nodes. Okay, now you got right what is node and what is edge. Hello.
Yes. Yes,
Okay,
Bhaiya.
fine. Now there are another like terms. We can distinguish this graph into directed and undirected. Okay, so what is directed and what is undirected? Let's take this graph. Okay, here the relation is bidirectional because we are not putting any arrow. Okay, the relation between this object and this object is bidirectional because we didn't put any arrows. Like this is a normal straight line. Okay, this type of graph is called undirected graph. Okay, suppose let's consider this graph. Okay, and so this is a graph. It has four edges and only uh, three edges, sorry, four nodes and three edges, and every edge is a directed. So this relation is from this to this only and not from like reverse side. Okay, so this graph is called the directed graphs. This is a one way to distinguish graphs. You understood what is directed and what is undirected, right? Hello. Okay, it's clear. So I just move forward now. Uh, Another way to distinguish graphs is weighted, unweighted. Okay, weighted, unweighted. Uh, let's take a real life example. So you people, like some people deposit money in different banks, right? Okay, so one person can deposit in multiple banks, or also not person and banks. Let's say different companies are there. So this is a company A. Okay, and this is company B, and this is company C, and this is company D. Okay, now company A have connections with C and D. Okay, and company C has only connection with D, and the company D has B, and B has only with C. So this is a graph, right? I just took random, and this is a directed graph, by the way, because all the edges are directed. Now connection means like there is a business thing happens over and there will be some money associated with it. So the transactions or amount maybe anything, right? Here I can say they have a 50K transactions between A and C, and between A and D they have only 10K, between this D and P 25K. So there is a relation, but there is a quantity also associated with it. This is called weight. Okay, the quantity that we are associating with each edge is called a weight, and this is called a weighted graph. Okay, or you can say now what is an unweighted graph? An unweighted graph is a graph in which all the weight of each edge is same, because there is no specific quantity associated with it, and uh, each and every edge is equally important. Okay, so that is called unweighted graph. Okay, is that okay? Weighted graph and
Yes.
unweighted graph. Yeah, so I told two ways now to distinguish these graphs. The one is by using uh, directed and undirected, and one is a weighted and unweighted. Okay, so any idea how we can store these graphs? Let's take simple. I just clearing this. We want to store graphs in the code while we are writing a code. Okay, how you store that graph in a data structure. Okay, so yeah, you have some nodes, you have some edges, and you need to store that in an data structure, right? Because you need to process it actually. So how you can able to do it? Any idea? Anyone of you can tell me. So we completed just first part. What is a graph exactly? Now we are just moving to representation thing. Okay. Hello. So
Yes,
no
Maya.
idea. Uh,
No, don't.
okay, fine, no problem. I just now how we can able to represent it is there are multiple ways to represent. One is using adjacency matrix. Okay, what is an adjacency matrix? So let's say the number of nodes is small n, the number of edges is small m. Okay, it is clear, right? The number of nodes is n, and the number of edges is m. What I'm doing is I'm taking n cross n matrix, or in programming language we can say 2D array of size n cross n. Okay, so I'm taking one example to explain this, and I'm taking a undirected graph. Yeah. Mm, and this thing. Okay, let's call it 1, 2, 3, 4, and 5, and I need to store this graph. Okay, so how many here? What is the value of n, and what is the value of m? Anyone?
5
Uh,
and 5.
1, 2, 3, 4, 5, 6. Right. So the total number of edges is 6, and n is 5. So what is the 2D array that I'm taking is 5 cross 5, right? Let's draw this 5 cross 5 array. Okay, fine. Now this is 1, 2, 3, 4, 5. But indexing starts from 0, 1, though that's we can take care of it. Just some writing for understanding. Okay. So if there is a relation between any two nodes, we just put 1 there, or else we put 0 there. Here see, there is a relation between node 1 and 2, so we put between 1 and 2 1. Okay, by the way, this is also possible. Okay, a node can have relation with that cells also. That's called a loop. Okay, so here we don't have any loops. So what should be this adjacency matrix? There is a relation between 1 and 2. So 1 should be present over here, and between 1 and 3. So 1 should be present over here, and 2 and 3. So here, 2 and 4 over here, 2 and 5 uh, over here. And one thing I missed out, it is an undirected graph. If there is an edge between 1 to 2, there must be an edge from 2 to 1 also, right? So here there is an edge between 1 to 2. So here also that should be present. And 2 to 4 is there. So 4 to 2 also present. And so I just write it. 1 3 is there. So 3 1. And uh, 2 3 is there. So 3 2. 2 4 is there. 4 2 is over. 2 5 is there. And 5 2. Okay, so yeah, so this is the total adjacency matrix for these graphs. Okay, do you understand this? Any problem over here? How we are doing it? We are taking the 2D array, and initially all are zeros. Okay, all are initialized with zeros, and we are just changing these two with one. How we can able to do? There is a relation between 1 to 2, so we can just do matrix M 1 2 as 1, and also at the same time m to 1 is also 1, so we can able to do like this, right? This is the final adjacency matrix looks like. Is that okay?
Yes, bhaiya.
Okay. uh, is there any property that you observe over here? Is there any property that you can observe in this adjacency matrix? Hello. Okay, so if you can observe, this is a symmetric thing. See, this matrix is symmetric. Like if you do the transpose, it's the same thing. Okay, so for an unweighted graph, sorry, unweighted, not unweighted, undirected graph, the adjacency matrix is a symmetric. Okay, that you can remember. Is that okay?
Yes,
How
bhaiya.
you can able to represent this mm, graph using adjacency matrix? Okay, before moving, again two terminology. Again, take a graph. Okay, this is a graph. Let's think 1, 2, 3, 4, and 5. Uh, Degree. The first terminology is degree. What a degree is? What is the degree of this node 1? The degree is the number of neighbors of that node. Okay, neighbors means uh, the nodes that is directly related to. Okay, here this 1 is related to 4, 2 directly. It is related to 3 also, but it is indirectly to through 2 and 3, right? So degree is the number of nodes that is connected directly with that node. Okay, here what is the degree of this 1? It is 2, right? And what is the degree of 4? 1, 2, 3. And for 2 it's 2, and for 3 it's 2. Yeah, for 5 it's 1. Okay, so you understand what is called the degree of a node. And neighbor, what is a neighbor? Neighbor is a node that is connected with our like concerned node. Here 1 is our concerned node, and 4 and 2 are neighbors to 1 because those are connected directly with 1. Okay, so in this way you can define degree and neighbor. Is that okay?
Yes. Yes.
Okay, cool. uh, let's talk about the complexity of adjacency matrix. We just uh, learned how we can represent graphs. Let's see the complexity of representing using adjacency matrix. Okay, so what we are doing, there is a graph, and we are creating n cross n matrix that's equal to mm, n is equal to the number of nodes. So here space complexity is order of n square, because we are creating n square number of slots, right? So the space complexity is order of n square. Okay, now what is the time complexity you want in this graph? Suppose you want, is there a edge between 3 and 4? So how you check? If you check just m 3, 4. If that is equal to 1, there is an edge, or else if that is 0, there is no edge, right? So for this, what is the complexity to check there is an edge or not? Anyone can? This is very easy. How you can check is there any edge between two nodes or not? You just need to do this. I just did. So what is the complexity to check this?
N square.
For this, it's order of
This
one,
is
right? Because yeah, this is an array. Okay, we are storing it in array, 2D array. Okay, and we're just accessing the element using indices. So why it's n square? It's just constant time, right? Order of one only. So for adjacency matrix, the time complexity is order of one for accessing the edges or to check an edge is there or not, and the space complexity is order of n square. Uh, I just mention a case, and you tell me adjacency matrix is okay or not. Okay, I have 1,000 edges. Okay, sorry, 1,000 nodes. Okay, like this, 1, 2, 3, and so on, and 1,000 edges are there, and there is only 5 edges present between them. Okay, 5 edges. Suppose this one node to 793 node is there is an edge like this. Only 5 edges are present. What happens if we use adjacency matrix over here? What problem that we face here? Can anyone tell me? Hello.
unnecessary checking of.
Yeah, here we are creating this much of space, right? N squared, order of n squared space complexity. For just 5 nodes, we are creating these many slots, and every like almost every node or every slot is 0 only. Okay, they're creating a 1,000 cross 1,000 matrix, and every slot is 0, 0, 0 like this, and only 5 are 1s. Okay, so if we use this thing, we are wasting a lot of space, and this is not recommended. Okay, so we need to think of another representation so that we can store this graph in an efficient way. Uh, if we have a less edges and more number of nodes. Okay. Uh, One thing you can remember, suppose you have a 2D array and there are a lot of zeros and only a few ones are present, then that matrix is called sparse matrix. Okay, so here uh, so this is a sparse matrix, and this graph is also called as sparse graph. For sparse graphs, if you use adjacency matrix to store it, it's a its space complexity is very high, and you are wasting unnecessarily very space. Okay, a lot of space. So we just need to think of a better way for this. Uh, the next better way, if we have a sparse graph, is list representation. You guys know what is a linked list?
Yes, Bhaiya.
Okay, so in this list representation, what we do is we have n nodes, right? We have n number of nodes, and we just create n linked list. Okay, or we can say yeah, n linked list. Suppose let's take a graph and try to understand this thing. Okay, this is a graph. Let's think, and this is 1, 2, 3, 4, 5, and 6. So I am just making 1, 2, 3, 4, 5, and 6. I'm making a 6 linked list here. Okay, this is a linked list 1, 2, 3, 4, 5, and 6. This is a head. Okay, there is nothing over here, and 1 is connected with 2, right? So here only 2 is present and nothing is there, so it's null. Okay, and 2 is connected to 4, 3, yeah, so 2 is connected to 3, and this points to next one. Next one is 4 and it's null. Now 3 is connected to 2, 5, right? So 2 and 5 and it's null. And what about 4? So 4 is connected to 2 and it's connected to 5 and it's connected to 6. Okay, yeah, only 3 nodes present. So in this way we do for every node, we just add a node if there is an edge, like we add that node in the linked list. uh, okay, here there should be no, not null. Okay, sorry. So this is a linked list and we just keep on adding those nodes into this linked list. Okay, if there is an edge between them, right? Do you guys understood how I'm storing this using list representation?
Yeah, got it.
Okay, so now let's again discuss about the complexity, when this is useful and when it is not useful. So what is the space complexity over here? Anyone just guess it, or like can directly say what is the space complexity associated with this type of representation?
Number of edges.
Order of
Number of edges.
number of edges. Okay, 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 okay. Yeah, somewhat correct. You just yeah, you were partially correct, not completely. Any other thing? Any other guess? Okay. So first of all, if there is an edge, there will be a node over here in linked list. Okay. So for every edge, there is an vertex in any one of the linked lists, right? For every edge, there will be a node in one of the linked lists. That's why M is definitely correct. And with M, these are the heads. Okay, these 6 heads that we are storing. So these why here 6, that is equal to the number of nodes. If we have a 10 nodes, we must have created 10 linked lists or 10 heads for this. So m plus n for this space also, so total order of m plus n. Okay, so what is the space complexity for this list representation is order of m plus n. What is the time complexity to check there is an edge between suppose I want to check is there any edge between 4 and 6. Okay, then between nodes 4 and 6, I need to check is there any edge or not. How you can do that? So go to the 4th list and check for 6 in this list. So traverse over here this list and you found 6, so there is an edge between them. So what is the time complexity for this? Any guess?
Edges.
That's order of n, right? Or yeah, it's a linear time, not exact here. I'm not mean n is a number of nodes. So what we are doing here exactly, we need to check uh, the edge is there between 4 and 6, so we are just gone to 4th linked list. This is an array of linked list, so we can just index it. There is no time complex for this constant time, and then we are checking these linked list. Okay, so we are checking this linked list. uh, Suppose we have a n number of nodes and m edges. So let's take average case and there is an equal number of edges in for each node. So what happens then? So number of nodes by n, like we have m edges and n nodes. So on average for each node these many number of elements will be there in that linked list, right? And this is not true for everything. This is an average case, just assumption. Okay, so you just need to traverse these many elements on average. So it's m by n. You can directly say this is like linear time. Okay, so the time complexity is linear for checking is there any edge or not. Because what happens for sparse graphs, the number of like edges is very low, so you can easily check there is an edge between or not, because you just need to uh, traverse one or two nodes for each and every linked list, because there are not a lot of edges. So that's approximately constant time. But for general graph, for any type of graph, so for searching is there any edge between two nodes, the complexity is order of n. Okay, is that clear?
Yes.
Okay, so this is space complexity and time complexity. So depending upon the context or depending upon the data that you have, you just you can choose any of it. So, and there is an other representation also that's better than these two. Okay, using hashing. So you guys know what is hashing? Okay, so do you know maps or dictionaries? Maps in case of C++ and dictionaries in case of Python. You know.
Yeah, yeah.
Okay, so what I'm doing is you can take graph and this thing. Okay, let's take this graph. 1, 2, 3, 4, and 5. There are 5 nodes, right? So n is 5, and what is m over here? 1, 2, 3, 4, 5, 6. So n is 5 and m is 6. Now I'm taking a map. Okay, so and in map uh, I I will do in Python, so I know more about dictionaries than maps. I can just mention what I'm doing over here. So for one, I will just make an array over here. Okay, and for two, I will take an vector or array for that. Okay, for three, I just take it. Now in this, there is an edge between one and two, so I will just push back this two into this. Okay, and for two what I'll do, I just push back 3, 4, and 5 also. For three what I will do, 2, 4. Okay, 2, 4, right? And for two and for four what, 2, 3, and 5, and for 5, 4, 2. Yeah, only two edges are there. So in this way I can store, right? So if you index it, suppose let's say this is a ADJ, this name is ADJ, and if you make this ADJ1, you will get this array, right? And in this array, you will have, or this is a vector, because you are adding, the size is not fixed, so that's why this is an vector. And if you search in this, you will get is there present or not. Okay, fine. Is this understood? Hello,
Yes, bhai.
till this. Okay, fine. Now, depending upon your purpose or your interest, you can, and depending upon the constraints also, and what is the data, you can take any of these three representations. Okay, while solving the problems. Fine. And what usually people do is in CP, okay, they just take two dimension like vector of vectors. you can understand in C++ language, vector of vectors. Okay, and how initially all are the initial empty vectors, and these empty vectors equal to the number of nodes. Suppose you have 5 nodes, you will just take 5 these empty vectors, and for every edge you will just push back into respective vector. Okay, suppose this is there is an edge between 1 to 2, you just push back 2 into this first, and 1 into this second, because this is a bidirectional I'm considering. If this is a unidirectional, you just push into one vector. Okay, because here you don't need to implement a lot of things, so this will be easy in CP. Okay, or you can what uh, as I before said, use maps for storing it. That's also a good thing. Okay, now we completed the representation thing, and also the some terminology or the important terminology of graphs. Let's see traversal. A graph is given and you are asked to visit each and every node. How you do that? I'm asking the brute force thing. Okay, how you traverse? This is a graph, and this is also possible. A node alone is also possible. There is no edge for this graph. Sorry, this edge. This is also possible. Okay, this is the graph. And now, how you would visit each and every node one time? Okay, there are two ways to do this. One is depth first search. Okay, and second one is breadth first search. Uh, this depth first search is called DFS, and breadth first search is called BFS. Okay, names is clear, right? Depth first search and breadth first search. So yeah, hello, any question?
No way.
Any question?
No way, yeah, no way.
Okay, okay, fine. So let's see first what is depth first search. In depth first search, what we do is we will start with any random node. Let's take this first node. I'm starting from this node. Okay, and what are the neighbors of this node 1, 2, and 5? Okay, so I can go to any of this 2 or 5. Okay, I just gone to 2. Now uh, I left 5. Okay, I mean I'm not considering this 5. I just gone to 2. And what are the neighbors of this 2, 3, and 4? Anyone I can do. So this is visited, this is visited, and for from 2 I can go to 3 or 4. So I'm going to 4. This one is visited, and now from 4 I can only go to 5. Okay, so I'm going to 5, and this one is over. Okay, now from 5 I can able to go 6. So from 6, is there anything to visit? Nothing. So I just go on to backward 5. 5 is already visited, so I just move to back 4. It is already visited, and I'm also again checking, is there any nodes, any neighbors which are unvisited for this node. For 6 there are no, so I just move to 5. 5 neighbors are 4 and 6. Is there any unvisited? No, all are visited. So I go on to backtracking 4. For 4, what are the edges are there? 5 only. 5 is already visited, and go to back 2. Now for 2 I left 3, so I come to 3. Okay, now 3 is visited. Okay, now is there is no, so I just move back. Here also there is no, I just move back. For 1, 5 is already visited, right? So everything is visited except this. Okay. Now after doing this, like I'm started with 1, right? I again need to start from 7. Here only 1. There might be a lot of things connected also. Okay. So I again need to start this breadth first search from over here, and from after it, all the nodes will be visited. Okay. So what actually I'm doing over here is I'm going to the depth as much as possible. First 1 to 2, 2 to 4, 4 to 5, 5 to 6. Okay, so I'm just moving, I'm going to the depth that is possible as much as possible, and after that I'm coming backward. And is there any suppose unvisited nodes, I'm just going to that way, and again I'm trying to move as much depth as possible. Okay, so this is called the depth first search. We are giving priority to depth, that's why it's depth first search. Okay, is that clear? Like there can be multiple ways to choose, that depends. Okay, anything is correct. From here 1, you can go to 5 or 2, and you can start the whole process from 5 also. That's not an issue. Okay, is this clear? Any question?
Yeah, bhaiya.
Can we start from the nodes which have only one edge? Then it will be more efficient.
One node here.
Okay, from the nodes which have only one edge or zero edges, and from then we can move towards the top.
But actually yeah, the time complexity is same only. Okay, we are visiting each and every node only once, so that's equal to order of n always. Okay, it will not increase. So I will write the code first, then you will understand why it's so. Okay, so dfs, this is a function, and we are given adjacency matrix. Adjacency, like what I mentioned here, maps. So there are multiple vectors in the this map. Okay, so that's what I'm taking. And visited array. So suppose n elements, 10 elements are there. I'm creating a 10 element visited matrix. So here initially all are false. Okay, all are false. And if a node is visited, I just make that true. If so, suppose the first node is visited, I make visited of 1 is true in this way. Okay, for this purpose, this is to check a node is visited or not. Hmm. Uh, After it, the starting node v. So you can give any starting node. Now what happens in this function? So initially you will do that node as true, because that is initially all are not visited only. Now you will check, you will go to any of the neighbor. Okay, for each neighbor in adjacency of v. Okay, you understand what this is? What is edge of v? This is a vector, right, which contains all the neighbors of v. Hello.
Yes, bhaiya.
For each neighbor in edge of v. Okay, if that neighbor, if neighbor is not visited, what you are doing is, okay, uh, you call dfs for that. Dfs adjacency, same visited matrix, and this neighbor you just give. You start like dfs from there. Here in the before example, you come to here, and you are going to next neighbor of this node. Okay, so why it is so? Because this is unvisited, so that's why you are moving forward. Okay, if the neighbor is not visited, you just call dfs for that node, or else you can continue. Okay, and Visiting means how you can able to know print that node. That's perfect, right? Print v. So that means you visited this node and then do this. And for every DFS, you can just do it. Okay. If the neighbor is not visited, you what you are doing, you are calling the DFS for that. And it is a recursive thing. So you will like visit each and every node if it is a connected graph. What is connected graph again? Another question. So this is a graph, and there is a lone edge, like there is an node which has no edges. Okay, this is an unconnected graph. A connected graph is that in that you can move from any node to any other node. Uh, like you can move. Okay, their length of the path doesn't matter, but you can able to move. Suppose you just consider this, you can move to this, and from this from this first node to you can move to this. So like this, that is there, that's a connected graph. If there are nodes, you can't visit them, so that's an unconnected graph. Okay, if you apply DFS for a connected graph, it will visit each and every node. Okay, for if you apply this DFS for unconnected graph, it will leave some nodes. Okay, because those are not connected. Okay, but we are only starting with single DFS, right? So this DFS is okay, right? What we are doing over here.
Clear भैया.
Okay, so if you do this, you will, I mean, in the console, you can see each and every node, but that is a random way. Okay, it's not fixed. Here 1, 2, 3, 4 is the node numbers. So you can see 3, 2, 1, 4 like this, any random, but you visit all each and every node. Okay. Uh, Now let's see some applications of this DFS. Okay. Uh, First one is connected components. Okay, connected components. What are connected components? Uh, for a connected graph, the number of connected components or CC equal to 1. That means how the connected number of connected components is equal to the how many times you need to apply DFS for it. Okay, so for this graph, this whole graph, how many times you need to apply DFS to visit each and every node? It's 3, right? Because for if you apply DFS one time, this all will be visited because these are all connected. And for this, you need to apply one time. For this, you need to apply one time. So total connected components is 3. Okay. So understand what basically is connected components, right? It is equal to the number of times you need to apply DFS for a graph. Okay.
Yes भैया.
Okay. Now, how you able to do this? Just do this. For every node in the adjacency matrix. Okay, so apply DFS for the first one, visited array, and this node start from this. And okay, before doing this, just need to check if this node there will be CC. Initially CC is 0. If a node is unvisited, if node is unvisited, then call DFS for it and increase the CC by 1. Okay, and after completing this DFS, it will come to this, right? This for loop, and you will check each and every node. So first you apply DFS here, and you will complete each and every node. And after that, this for loop goes here. This is already visited, this is already visited, this is already visited, and it comes here. This is unvisited. So CC will be increased by 1 again. And it will this DFS will complete in one step. Again, it comes to this for loop, and it comes to this, and this is also unvisited. So CC will become 3. It increases by 1. Okay. So finally, return the CC. So that is, you got right how to calculate this connected components. Same DFS you are using here, and remove that print thing, because you don't need a print thing, right? It's clear.
Yes, got it.
Okay, so I will just show you one problem. Okay, we'll try. Yeah, this is a problem. See, this is a problem from hacker actually. It's for finding the connect number of connected components. You can just try it. Okay, it's loading. Why it's very slow. Okay, it's loaded. Hmm. Read the problem. Given n, that is the total number of nodes in an undirected graph, undirected it is, and numbered from 1 to n. Undirected means that is bidirectional edges are present. If there is an edge between 1 to 2, and there must be an edge from 2 to 1 also. Okay, and an integer, that is the total number of edges in the graph. Calculate the total number of connected components in the graph. A connected component is a set of vertices in a graph that are linked to each other by paths. Okay, so the input you can see the first line contains n and d. N means the number of nodes, and 5 means the number of edges. And here the edges are given. Here 1 to 2 edges given. That means you need to consider 2 to 1 edges also there. Here 2 to 3 is given. That means 3 to 2 is also there. So how you store this, that depends upon you. One way, what I usually do is, I told that is a dictionary of vectors, or map containing the vectors. Okay, each node number is mapped to a vector, like that I will do. Okay, and then you apply DFS, and I shown just how to calculate DFS and print that out. Okay, try this. And for the Python, who uses Python, you just need to see the recursion limit. In Python, the recursion limit is set to like low number, some, and for last test cases it will fail. So you manually need to increase the recursion limit and then do that. For C++, it's fine. You won't face any problem. You can just, you will get accepted. Okay. So try this. This problem is in HackerRed. Do you need a link for this? Okay, I will just post this link. Yeah. Try this one. So now the next application is bi-party. Okay, bi-party. What is bi-party is, a graph is called bi-party. So if you can divide that graph into two set of vertices, or two set of nodes. Suppose a graph is there, and you can distinguish that graph into two set of nodes. uh, Suppose here four nodes are there, and here three nodes are there, and edges are only present between these two sets. Okay, that means there is no edge between like two nodes that belongs to same set. Like this one is not possible. Okay, you understand, right? What is a biparty means? So no edge is possible between two nodes that belongs to same set. That belongs to same set. Okay. Or in other words, if you color this all the what happened? Someone wants, yeah. If you color them using two colors, like let's suppose red and blue, so all the vertices will be like divided into red and blue, and there is no edge between two red nodes, and there is no edge between two blue nodes. Then that graph is called bipartite. Okay, clear, right? What the definition of bipartite?
Yes.
Okay.
Yes, we have.
Now, how you check given graph is bipartite or not? So this is the question. So we can do that using DFS. This is another application of DFS. By using DFS, you can do. So here, along with the visited array, you just like two colors, right? So let's say this red is 0 and blue is 1. Okay, binary thing. Red is 0 and blue is 1. I'm just uh, like applying this, modifying this DFS little bit. Okay, adjacency matrix is there and visited matrix is there. The starting node V is there, and initially the starting node I'm just coloring it with 0. Okay, so uh, let's say this red. Okay, red means 0. While we are calling the function, we pass r as 0. Okay, now first we make this as true because that's visited, and now what we need to do after it? For every neighbor in adjacency of V, that means that neighbors of this node V. Okay, uh, if it's not visited, if it is not visited, what we are going to do is, okay, okay, here we need another array also, that is a colored array. Color array means suppose we have 5 nodes, and this colored array will have color array, name is color, 5 slots, and uh, each slot is for the color of that node. Here we are taken the first node color as red, right? So it will contain r or 0. Okay, we'll update this whenever we are like doing this. Okay, 1 0, it might be there, like 2 sets it will be there, only 0 and 1 is possible. Visited of V is true, and again color of uh, this V is equal to this color r. Okay, and now if it not visited, you just if DFS not DFS of adjacency matrix visited array. Again, now this neighbor you need to pass, and here 0. Okay, that means you need to send the complement of that, right? Because there is an edge between that, so you need to color that node with the complement. Okay, so complement of r or not of r. Okay, and this colored array again. Now return false. So you are checking the graph is biparty or not. So there is only two return types are possible, either true or false. So you are checking here, applying. If it is a false, then you are returning the false. Okay. Okay, if not DFS means if this output is suppose false, what happens of not false, it will become true, then it comes into this if block and it will return false. Okay, for this purpose I took this not, and if not DFS, I just return false, or if it is not visited, this is happening. Okay, suppose if it is visited, that means else. Check it. The color is same, that means it's not a biparty, right? If color of this node v equal to color of the neighbor, that means it is not a biparty, return false. Okay, that's what you need to check. And if you completed everything and you don't face any problem, and finally you just return true. Okay, if you won't face any problem, then like here also this DFS is true for every not visited node, and this is also true if a node is visited. Okay, then it will, this for loop will complete and you finally return the true. So this is what you can tell a given graph is a biparty or not. Okay, it's called a biparty checklist. Is that okay? Hello. Hello, guys, is that clear or I need to explain it again?
Clear.
Okay, okay, I got it, fine. So for this also I have a question. You just try it out. So read this question once. Professor Hopper is researching the sexual behavior of a rare species of bugs. He assumes that they feature two different genders and they only interact with the bugs of the opposite gender. In his experiment, individual bugs and their interactions were easy to identify because numbers were printed on their backs. So given a list of bug interactions, decide whether the experiment supposes assumption of two genders with no homosexual bugs or if it contains some bug interactions that falsify it. Okay, what happening here is uh, bugs are there, and you know male bugs and female bugs, and there is an interaction between them. If you can able to divide them into two sets, okay, uh, like if that graph is a biparty, then there is no homosexual bugs. If there is an edge between two bugs which belongs to the same set, then there are homosexuals. That's what here you just need to like check if the graph is a biparty or not using the DFS. Okay, now same thing here. The first line of the input contains the number of scenarios. Okay, each scenario starts with a one line giving the number of. Now here the interaction is given. Okay, so output suspicious bugs found. If you found the graph is not biparty, or else no suspicious bugs found. That's the thing just you need to print. Okay, try it out. I wrote the code also, like I wrote pseudo code. Just implement it in whatever way you want. I'm uh, giving this link also. Okay. Yeah, I just Subhashish, I just send this like connected components one. You can see it. Okay, I will just post it again. Wait. Okay. So this one, first one is a Bugs Life one, and second one is this connected components one. You just tried both of them. Okay. Uh, I explained two basic applications of DFS, and there are a lot of applications of DFS. One is you can check there is a cycle in that graph or not. What is a cycle? You know, right? just showing it. So different nodes are there, and if you start from this node and you can able to reach that node again, there is a cycle present. Okay, so you can able to detect the cycle also by using the DFS. You just like do research on your own and you can learn it. Okay, I explained the basic things. So traversal DFS is completed. The basic things are completed. And if you want, you can go further, and there is no end for graphs. A lot of things we need to study. Okay. The last thing I will do is BFS, and in the next session, graphs 2. Okay, there will be some advanced algorithms of graphs will be discussed. Okay, some next algorithms that will be discussed. Uh, what is BFS? That is breadth first search, right? Breadth first search. Okay. Now, again, let's take this example. 1, 2, 3, 4, and 5. So in breadth first search, you can start with any node. So I'm starting with from 1, and you traverse all the neighbors of it first, then only you move to the next one. Okay. So in depth first search, we are going to as much as depth possible, but here it's not like that. You are first completing each and every neighbor of that node, then only moving to the next node. Okay, so first you visited this thing, and you visit this thing and this thing. All the neighbors are completed. Now check for this first first neighbor 2. Is there any neighbors which are not visited? No, all are there is no neighbors. Like neighbors are 1 and 3, they are visited. Okay, now move to 3. So for 3 there are nodes which are unvisited, that is 4, okay, and 5. These are visited both, and there are nothing. So now you check for 4 and 5, there are no, so it is completed. Okay, in this way. So I will just write the code, then you will understand. BFS, there is an adjacency matrix over here, and again visited matrix and starting node V. So initially we will make visited V is equal to true like before, and print that node, because you need to know is that visited or not. And then okay, uh, for every node for the here I'm taking a queue. Okay, queue, this is initially empty. Okay, for each node in this adjacent of V. Okay, uh, if not visited, that node is not visited. Okay, you add that into queue. Sorry, queue dot add this node. Okay, because for again you need to apply BFS for this. Okay, that's why you are adding it into queue, and else you just print it and make that node. Sorry, not V here, it's node, right? Print that node and visited of node equal to true. Okay, after completing this, uh, again you pop this queue, again start this process. If queue is not empty, if queue is not empty, again go from here and start. Okay, so in this way, like, or you can say go to this line number, suppose 6, so go to 6, like that. Okay, you can implement this, you understand the basic thing, so you can implement this by using in own your own language. Understanding this algorithm is important. You got this right? What we are doing in BFS, we use queue for it. So what happens in queue is, so you are visiting 2 here, right? So but you didn't apply BFS for 2, so you are adding this 2 into queue. Okay, and 3 also you are adding this into queue, and because that is unvisited. Now for 1 it is completed. So what is there in queue now? 2 and 3 is there. So the process starts with node 2. Okay, and there is no unvisited, so there will be no elements added to this queue. So 2 will be popped and 3 is there. Okay, now again start the process from node 3, and after this 3, 4 and 5 will be added, and you just pop 4 and again start with the process with 4. In this way all the elements will be visited. Okay, so for that this queue is used, right? Yeah, any questions, or we can just end the session? Hello. You try to implement this PFS and DFS, or else you will forget it. You will surely forget it, that's for sure. And do some problems with it, and study other applications of DFS and also some applications of BFS also. uh, in the next session we'll try to complete the applications of BFS also, but if not possible, uh, we will discuss some important algorithms of graphs. Okay, fine, right? Okay, cool, done. So I'm just stop sharing and also stopping the recording.